Okay, so good morning. Today I will show you my work that basically I did in these 2 years. So my focus is on OMA, operational model analysis. We could describe operational model analysis as the process to obtain the model parameters of a structure, basically using vibration response only. So using acceleration, displacement, and velocities in order to get frequency, damping ratio, and model shape. We have a lot of methodology that we could use in OMA. For example, basic frequency domain decomposition, and stochastic identification. From all the methodology, I decided to I decided to use the last one.
You can press save, no?
I don't have anything on the screen. What is that? Okay. Let's switch the one thing. Okay, perfect. So I decided to use the last one because it's the one that allows me to obtain the better result in an automatic way. And from the middle of SSI, I decided to choose the covariance-driven stochastic subspace identification because I obtained the best result with the lower computational effort. So, very quickly, mathematics. As we all know, a linear system is described by the classical equation of motion, where M, C, and K are the mass, damping, and stiffness metrics. U is a vector containing all the invariant input, while B2 is a matrix that distributes all the input to the varied degree of freedom. As some mathematical steps, we obtain the state space model, in which the first equation describes the evolving of our system, while the second one basically describes the measurements. But I said before, in OMA, we don't know which are the input, so the term BUK and DUK became the term WK and VK, where VK is the process noise that accounts all the problems that we could have in the model, while the second one is the measurement noise that is linked to all the problems that we could have during the measurements in general. So we have also 2 very important metrics, the A, that is the state matrix, and C, that is the discrete output matrix. From the first one, from the A model decomposition of A, we could obtain eigenvalues that allow us to obtain frequencies and damping ratio, while using the eigenvectors and the matrix C, we could obtain the model shape. So in order to obtain ANC, we need to calculate the covariance matrix that is formed by all the covariances between all the signals. We have a first problem, because to obtain the real covariance between all the signals, the length of this signal should be infinite. So obviously this is not possible. So we just get some estimate of the covariances. Also, science by hypothesis, we should assume that our system is controllable and observable. We could divide this matrix in the observable matrix and controllable matrix. Also using a singular value decomposition, and then equating these 2 equations, in general, we could obtain A and C. So here we have the 2 most important parameters that we had to use in order to do our identification, that are the time lag E, that is showing the covariance, and that is the called model order. Let me see what this means. Here we have 6 different plots. In the first row, we have the value of the singular value obtained from the SVD compared to the model order. In the second row, we have the subdivision diagram. Those diagrams are very useful because it allows us to discriminate between real and spurious frequencies by looking at the straight column of stable poles. We could define a pole stable, which it passes some criteria, on damping ratio, model shape, and frequencies that are set by the user usually. So what we see is that in general, the information about this identification method is carried out by the non-zero singular value obtained from the SVD. So in the first case, for example, that we took a lot of zero value, we could see that the results are very poor. While in the third case, in which we are not considering a great number of different zero value, in general, we have results, but not so good, as for example in the middle one. So the right choice of the time lag, in this case, I fixed a model order and I use different value of time lag. Is very important, the right choice of time lag. Also, the choice of model order. In this case, in this free subdivision diagram, I fixed the model order, the time lag, and I vary the model order. So if it's too low, we can see that in the first case we don't get basically any information. While if it's too high, a lot of spurious mode will appear, and the identification will be very difficult. So I will show my research basically in this moment, at least, it's focused on the finding a good value of time lag and model order. I will show you some examples that I used during these 2 years. The first one is a beam implemented in MATLAB. The second one is experimental beam, and the third one is a bridge set in Florence. Let's start with the MATLAB beam. This is a very simple beam fixed at the base, in which we imagine to use for different monoaxial velocimeters. So the first thing we did is to do a simple model analysis in order to get all the frequencies of this beam. Then we generated a white noise in MATLAB, and with the new mark method we obtained with the velocities, and with the velocities we run the curve SSI. So here we have a first attempt to see what different value of the model order will bring. As I said before, in the first case, we have very poor civilization diagram in which we lack some information, while increasing that, even in this very simple example, in the first case, we have the present a lot of spurious mode, and it will obviously make the identification more difficult. Later, I tried to find a method to discriminate between, in the case that we have two closed modes. So the first thing that I use is the MAC. MAC is model assurance criterion. It's an index that goes from 0 to 1. 0 when we have two orthogonal model shape, 1 when we have basically the same shape. So as you can see here, in frequency, if you look at the frequencies of 571 and 572, we have a very big value of MAC. So it means that they are basically the same frequency, but we need a way also to better understand which one of the two we want to discard, obviously. For doing that, we could look at the damping ratio. In this case, I didn't model any damping, but if you look at the frequencies of 572, we have damping. So for this reason, I discarded this frequency. Now we try to repropose basically the same thing, but on a real beam. So we use this fixed beam, steel beam, in our laboratory in Catania. The first things we did was we could use for different accelerometers. So the first things we did was to find a good position of the accelerometers. In general, we try to avoid the node because the node will not bring any information. And then we carried out for different schema. In this case, we used two triaxial accelerometers that was put on the high part of the beam, and two monoaxial accelerometers. The triaxial accelerometers were attached to the beam with a adhesive mounting, while the monoaxial were attached with the screws welded in some defined points. We did the code, and we saw that the best scheme to use was the second one, basically. So with the code, in this case, I use a very, very high value of both of time lag and model order. As you can see here, the stabilization diagram is very confused. You cannot get very well the frequencies of the beam. Anyway, we got some frequencies. Also, we did the FEM model to compare the results, and basically the frequencies were the same. Unless for two frequencies, 11.90 and 43.22. So again, if you look at the MAC, in this case, this is not very useful because the value of the MAC is very low in general because all the frequencies are distant. But if we simply look at the model shape, we can see that the frequencies at 11.9 and 43.22 are basically non-real frequency modes, because obviously the model shape are not real. And this is also reconfirmed by the model shape, by the damping ratio, in which the value of the damping ratio is very high. So we could say that we can, if compared to the other one, we can effectively reject these frequencies as real. Okay, we here had a problem. I don't know why. So with these two very simple examples, I wanted to show you why the right choice of time lag and model order is very important. So again, I focused my research on trying to find a methodology that allows me to do that in an automatic way. The first step was to define a reliable vector. What is a reliable vector? It's a vector that contains all the most probable frequency of the structure, because we need to know in the case we don't have any information on the structure, we need to know which are the most probable frequencies, obviously. For doing that, I used a Monte Carlo analysis in which the time lag at the model order could vary besides some bounds to collect the most frequencies, the most recurring frequencies. But at the end, I also need to define a threshold in order to identify those frequencies. So I tried this methodology on this bridge. That is a bridge, as I told you, sited in Florence. This is a very old bridge built at the end of the 19th century. It presents a lot of damage and also corrosion. So for all this reason, we started a monitoring plan, a long-term monitoring plan. The bridge is made by steel, has a length of 27 meters and a width of 44 meters, and it's formed by 9 steel arches that are all hinged at the end. So we used 17 different triaxial accelerometers put on 5 of all 9 of all arches for a total of 51 recording channels in all 3 directions. But we also used 6 inclinometers that was put all in one of all the arches, 20 strain gauges, and a total station to get all the possible information of all from the bridge. All the accelerometers are connected via Wi-Fi to a central unit. From the central unit, the recordings were sent to a web platform from which it's possible to download all the records. We use a tempo rate of 160 Hertz, and every hour we have a length of basically 50 seconds. So we have a lot of records that are available from the web platform. You can also check if some of the accelerometers are working correctly or not. as I told before, I need to define some bounds in which the time lag and the model order could vary during the Monte Carlo analysis. For doing that, the first things that we need to do was to obtain which is the first frequency of our structure. For doing that, I implemented a very simple peak picking method, and as you can see here, the first frequency found was at 5.85 Hz for this structure. Then I defined the bound in which the time lag and the model order could vary. The lower bound is chosen in a way that at least to obtain the minimum information of the structure, while the higher bound is chosen in order to not increase too much the computational effort of the of this phase. I mean, this is very, very high. So in general, I run from 50 to 100 Monte Carlo analysis, depending on how much time I have. Every run, I obtain the frequencies, the damping rate, the model shape. But at the moment, I'm working only with the frequencies, because using model shape and damping ratio could be a little bit tricky. So I collect the frequencies from every record, from every Monte Carlo analysis, but also from every record we would see, and analyze it first with a CDF, and then I derive the CDF in order to obtain the PDF. The PDF is very useful in this case because it gives us some information on which are the most probable frequencies of the structure. But here I needed a way to automatically choose which are effectively the most probable frequencies without because obviously this automatically, because obviously this PDF could vary, and I cannot be there always to take, okay, this peak, this peak, this peak. So for doing that, the first thing was to obtain a commodity distribution function that could fit all the peaks in the PDF. So I took all the peaks on the PDF, I calculated the CDF, the experimental CDF, and I tried to see which one to find a good CDF to fit this value. In the orange line is a normal CDF, while the blue one is a beta PDF. So here we have 4 different plots from different records. And as you can see here, in every case, the best fit is the beta distribution. So I decided to use that one. Then I estimated the parameters of the beta PDF, and using an inverse beta distribution, I defined a threshold in order to collect every time the most probable frequencies. So I did this with a very varying value of the percentile, as you can see in the label. With a high value of the percentile, we basically don't get any frequencies. And if we lower it, we get all the frequencies that we want, but we have to pay attention to the point because we cannot lower too much, obviously, the percentile, because we will get all the frequencies, and this is not what we want to obtain, obviously. So in this way, I did this also for more records in general, and I collect all the most probable frequencies in order to form the variable vector. But why doing that? Because after that, I rerun the Monte Carlo analysis, saving the value of the time lag model order, and compare the results of the frequencies obtained with the new Monte Carlo analysis with the reliable vector. The time lag and the model order that are more the greatest similitude with the reliable vector are basically the best one. For doing that, but for doing that, I first needed to define some metrics, obviously, to do the comparison. And as we will see in a few slides, the results that I will obtain will be very spread. So I also need a way to, in some way, finding fit the best pair of time lag and model order. Those are the two metrics that I used. The first one is the Malamobis distance. It is basically a distance that told us that measure the distance of a point to a distribution. It basically gives us a measure of how many standard deviation P is far from the distribution. The second one is cosine similarity. It basically measures the angle between two vectors. It's very useful because it not depends to the magnitude of the vectors, but only on the direction. So when we have a value of 0, we have a bad similarity. When we have from 1, we have a good similarity from the vectors. Those are the results that obtained. Every point is a pairs of time lag and model order that are considered acceptable in this way. But as I told you before, you can see here that the value in general are very spread. Following the principle of parsimony, I tried to find some frontier, some Pareto points to fit all the acceptable value, and trying to maintain a low value of time lag model order in order to not increase too much the computational effort of this phase. So the first thing I did is to implement a k-mean clustering in order to get the most external point. In this phase, the user could choose which cluster it use, to reject one, to take someone as you want, basically. Then I use a convex pool algorithm. This is very, very simple algorithm in which I get the smallest convex set that enclose all the points. So this is a very simple method to gather all the external points and to collect them. In this case, I decided to use the first three convex pool. And then I fitted the points that I found in this way with some spline, smoothed spline. So here you can see that basically the points, the fitted points are not so different with the two methods that I used. And also it's very good fitting. Very good fitting. And what I did then is to discretize the points in this line, basically, and see what I obtained with this method. Here you have the results. You could see the results. In the histogram, the blue one is the result obtained with this methodology, while the red one are the value obtained with the reliable vector. As you can see here, we basically obtain the same value obtained in the reliable vector. So we get the most probable frequencies, but with decreasing a lot the computational time. Also, another thing that's important to remember is that the result will depend a lot on the records that we are using. So I tried to use another record. Here we can see that the results are even better. So we have a very good way to find this point to obtain the results. The results are quite good. So we could use this methodology basically. In conclusion, the algorithm allows the computation of the process, eliminating the need for the user to manually select the frequencies individually, to avoid the problems related to the choice of time lag at the model order, and to define optimal values of time lag and model order. Also, significantly reducing the computational effort. The method rely on a preliminary phase that cannot be avoided. The accuracy of the preliminary phase depends on the number of iterations in a Monte Carlo analysis, requiring significant computational efforts. Also, if the ambient version is too much noise, the results could be wrong, which can affect the overall results. As future development, I think to implement the calculation of uncertainties in order to define relativity bounds in which frequency could vary. Also, find an automatic way to distinguish between the cases that are too close frequencies, because at the moment it is not automated. So the user should be there checking at the Mac and see, okay, these are the same, those are not. And in the end, improve the preliminary phase, reducing the computational time, maybe trying to avoid in this phase the Monte Carlo analysis. Thank you for the attention.